Hello and welcome back. Now it's time to start a new chapter with the title Coordinate Systems in Geodesy. But our main focus is on terrestrial coordinate systems. Let me start the discussion with some basics. For example, a two-dimensional planar coordinate system. Consider point A. If I project this point to the x-axis of the system and the same point to the y-axis of the system, I get these two projections. The distance from the origin and this projected point on the x-axis is called x-coordinates. And similarly, the distance from origin and the projected point on y-axis is called y-coordinates. I can define the coordinate for the point A in another way, using a distance from the center of the coordinate system or origin and one angle. Therefore, the coordinates of this point can be determined by x or y coordinates, which are known as Cartesian coordinates, or with the distance and angle, which are known as polar coordinates. And the question is how to convert these two coordinate systems to each other. For example, let me start with this polar coordinate system. Polar coordinates that I want to convert them to the Cartesian coordinates. To do so, look at here. We have a right angle triangle here. And if I have R, as you see here, and I have alpha, the angle alpha, it is simple to see that x will be R cosine of alpha. And y will be R sine of alpha, which is the side in front of the angle. So with a simple trigonometry, we can convert the polar coordinates to Cartesian coordinates. But what will be if you have the Cartesian coordinates and I want to convert them to the polar coordinate, what can I do? Again, I use the same principle that I use for the Cartesian coordinate, for computing the Cartesian coordinates. But the difference is that in that here, I have x and y. But the unknown parameters are r and alpha. So if I want to determine r, so I have x and y, and based on Pythagoras rule, I can say, okay, this r is square root of the sum of the squares of two other sides of this triangle. And alpha simply can be determined by the arc tangent or tangent inverse of this angle alpha, because angle alpha is y, the side in front of alpha, over the side of the alpha, which is on the side of the alpha. So we can determine the polar coordinates of a point using the Cartesian coordinates as well. Now let us add another dimension to our coordinate system. In this case, we will have a three-dimensional coordinate system. And the point A is projected to the x, or and y plane, and the projected point is again projected to the axis x and y. And similarly, we can say that the distance from the origin and this projected point here is called x, and the distance from the origin and the projected point at the y-axis is called y-coordinate. And how much the point has been continued downward to this plane, this size will be actually the z-axis of the coordinate. So the coordinates of a point in a two-dimensional coordinate system can be presented by three coordinates, x, y, and z. Similarly, this coordinate can be determined by a distance from the origin And if this is the projection of this line to the x or y, the angle phi from the x-axis and an angle beta from this point on y-axis. It says how much it should go up. So the coordinates of the points in the system can be Cartesian or polar coordinates. And in polar coordinates, again, we use angles. Then if we use angles, it's called coordinate. I have seen that there's some places they say that it's a curvilinear. What I say is polar for me. It's much more appropriate in my opinion. But the question is how to convert the polar coordinate to the Cartesian coordinate. The principle is very simple. Consider that this line P here is actually projection of the row this side to this. And we have a right angle triangle here. And here is 90 degrees. Therefore, if I have the bit beta, which I suppose that I have this, and I have rho, which I suppose that I have that, therefore, this projected line, which I showed by P, is rho cosine of beta. So this side is now. Now, the next step is to project this P to the x-axis. How? Look, we have a triangle, right angle triangle here. And I have this angle alpha because I suppose to have alpha because I want to go from the polar coordinates to Cartesian. Then polar coordinates are known. So if I have this side and I want x is enough that I multiply P by cosine of alpha to get x. Yes. And if I want the side in front of it, which is actually equal to y, therefore it's enough to multiply P by sine of it. In order to determine zeta, or how much we should go down. So I have a triangle here, which is a rectangle triangle, and this angle is 90 degrees. And if I write, we have this side, and I have beta, and this side will be, or that will be this side cosine of beta. So in that way, we can convert the polar coordinates to Cartesian coordinate. What about the opposite? If I have Cartesian coordinates and I want to get polar coordinates, the principle is again very similar. We use the same triangles that we have used so far. So, but this time, since we have assumed that x, y, and zeta are known, in that case, this P, this side, will be square root of the sum of the squares of x and y, based on Pythagoras rule. So if I have this side and I want, for example, rho, that's enough that I have this side the squares and plus this side the square, and I take the square root of the result and I get rho that way. So in order to obtain beta, I have P side and I have zeta. I know how much I have come down. The tangent of this beta is the side in front of the angle over the side, which is on the side of it. Then you get beta here. And alpha can be determined similarly. So tangent of alpha is the side in front of alpha over the side which is on the side of. And if I take arctangent or tangent inverse, I can come to angle alpha. That's the way how to convert Cartesian to polar and polar to Cartesian coordinates in a three-dimensional coordinate system. Spherical coordinate system is very similar to the three-dimensional coordinate system. The difference is that we have a sphere as a reference. Consider a point outside this sphere. I project it to the x, o, and y plane, and the projected point is again projected to x and y axis. And as I already mentioned, the distance from the origin and this projected point is the coordinate x, and distance from the origin to this projected point on y-axis is coordinate y, and how much we have come down from A to this, or the projected point of A to zeta is called the z coordinates of the system. Also, we can define the coordinate in another way. So, the distance from the surface of this sphere, which we show with h, and we already know that the radius of the sphere is, for example, r. And again, we need this line for definition of the coordinates. And this phi is actually, this is the same with geocentric latitude. It's the angle from the x, o, y, and this direction of point A from the origin. And also this angle lambda, which is the longitude, the angle between the x-axis and this projected direction here, which I show it by lambda. So in a spherical coordinate system, the coordinates are also defined in the Cartesian form and polar form. And the main point is how to convert them. Now consider that the polar coordinates are known or are given, and we want to determine the coordinates, the Cartesian coordinates. The principle is extremely similar with what we did in a three-dimensional coordinate system. But here, instead of rho that we already have, we should consider summation of r and h, as you see here. The rest is very similar. So I don't repeat this one here. And also, if I want to change the place and I want to determine the polar coordinate from the Cartesian coordinates, again, this principle is similar. But the point is that we, in that case, consider that h is the main point, not the whole distance from A to the origin. So if we consider the Pythagoras rule for determining this rho, we have to subtract r from that so that we can get the height over the sphere. Lambda has the same formula as before, and phi or geocentric is very similar here. Exactly based on the Cartesian coordinates, we can say that this side is the square root of some of the square of the other coordinate x and y, and zeta or z we have here, and this angle tangent of this geocentric latitude is this side over this side. So the phi angle will be the arc of this zeta over the side of P, which is here. So it's very similar to the three-dimensional coordinate system, but it has similarity to the geodetic coordinate system, which we will discuss this later.